Um, okay, look, check it out. For you, you can go to YouTube and you can see, you just pause it there so you can see the work that we did there. And there, there, you can pause it there to see the work we did there. All right? Sorry about that. All right, so today we officially get into the words eigenstates and eigenvalues and whole eigensystem. So eigen is, depending on who you look at, translates slightly different, but it's a German word that says its own or the one. What I learned is the one, so if you're a fan of The Matrix, Neo was eigen. Just, so you can appreciate that from now on. Proper state and proper value is another translation, which is what I probably am going to refer to if I ever try to translate it. So you have the proper state and the proper value. It's the one state that you get. The words eigenstate, eigenvector, and eigenfunction, these words here, are the same thing as your stationary state, which is the, we've been talking about our different solutions to the wave equation, the wave functions. Each one of those wave functions, since we were doing the time independent, was a stationary state. So that's why I've been using these words, because they really are the same thing. So eigenvector is using the emphasis on, like our kets are vectors for a state. Eigenstate, of course, I just said for a state. And eigenfunction is thinking then about the wave function instead of the vector, but it's still defining the same thing. And stationary state. So I'm sorry that I've been using that word when it hasn't been introduced. And I've tried to wave my hands. Just like I started using the Dirac notation before we got to it, because it's just sometimes a lot quicker to write. And we use those a lot. Now, an operator, when it acts on a single eigenstate, should give you a single eigenvalue, a single result. So that's what the eigensystem is about. You have a state, you have an operator on it, and you get the single value that comes with it. Now, there is another word here that's super important, degenerate. Degenerate does not mean, if I were to say that insert name here is a degenerate, that wouldn't be a good statement, right? It's not a bad thing when we talk about an eigenstate being, or an eigenvalue, being degenerate. What that means is it's possible that you have multiple states that give you the same eigenvalue. So for instance, let's take something you know well. A hydrogen atom. You can have 2 electrons in the ground state. So that's degenerate because you have 2 different states actually, but the same energy. So that's what we mean when we have degeneracy. You have, that's an energy degeneracy. You have 2 different states that have the same energy. And so that's going to be an important thing for us to think about as we move on. So these words here are important ideas, and it's important to know what degenerate means. So here's just some brief descriptions of the properties of eigenstates. Eigensystems. I said eigenfunctions here. Remember, eigenfunction, eigenstate, eigenvector, all the same. They correspond to different eigenvalues, are orthogonal. What does it mean to be orthogonal?
Mutually perpendicular.
Okay, mutually perpendicular. So if you have eigenfunctions that correspond to different eigenvalues, they're going to be perpendicular. Eigenfunctions of the Hamiltonian form make complete set. What does it mean to be complete?
So to have every possible, I don't know what to call it, every possible set of vector.
At every possible direction, let's say. If it was a three-dimensional vector, it'd be every possible, there's only three independent directions. What we say is it spans all space, but you have to know what spans all space means conceptually, otherwise you're just saying words. And then eigenfunctions can be normalized. Now, as we go through, we're going to find something that's not normalizable, and then we're like, oh, what is it? And the answer is, well, it must not correspond to a stationary state. Every operator is going to have its set of eigenstates. So far, we've been using the Schrodinger equation. That's the Hamiltonian operator. And so we've been finding the eigenstates for the Hamiltonian operator. And we've been finding the eigenvalues for the Hamiltonian operator, which are the energies. So it doesn't have to just be the Hamiltonian that you find a wave function for. You can find it for any operator. And this statement here, these are, if you look at them, you see that, yes, those are the same equation. It's just subtracted q psi across and then factored out the psi. But this is going to be something that's important when we look at these as matrices, because we're going to look at the operator as a matrix, and then that q is the eigenvalue. And so we're going to make a matrix calculation and find eigenvalues for an operator. And then from that, we'll find the eigenstates using this relation. So the lower relation is going to look like a new equation when we actually get to doing that. But recognize that is just operator Q acting on wave function psi gives me observable value Q times psi. Right, both of those are simply saying that. Something we've been doing all along, right? We did P operator acting on psi gives me P value times psi. I think on the first test you had to do something like that. And so here, just showing the same relationship with the Hamiltonian. And now we get to do something, some calculation. This is the thing that actually is somewhat relevant to that homework problem. I said we need to get to it. So P operator, the P operator is minus IH bar ddx. And so what I want to find is the wave function for that P operator. And so by definition of the eigensystem, my P operator acting on its, whatever its eigenfunction is, needs to give me my P value. So that's why this P doesn't have a carré or a hat on it, times the same function. So I'm simply going to replace the operator here with what it is. So now I have a differential equation. IH bar ddx of the function is equal to P and then times the function. Now you all have a fair amount of calculus under your belts. This is an equation you can solve. Even without differential equations, this is the level of differential equations we can solve, just like we talked about in class earlier today. So what do we do to solve this to find f of P? Separate variables. So what are the two variables? That's probably the hardest question of this problem. The function, right. The function and x are the two variables. And so to separate variables, I'm going to multiply both sides by, well, divide both sides by minus IH bar. And multiply both sides by dx. And divide both sides by fp. And I'm not going to put the parenthesis of x. So that's three different math steps in one, just to make my life easier. And I'm going to have df sub p over f sub p on the left side is equal to IP dx over h bar. Did I do that right? So now we integrate both sides. And this time around, I didn't even bother to put limits. And on the right-hand side, it does feel a little bit awkward. A little bit awkward because are P and X independent of each other? Yes. But it doesn't feel that way usually. So now I can solve for f of P. What is f of P equal to? Did I miss a sign? Because I could have sworn it. This is, by the way, I'll go to the next one and we'll see if I made a mistake. This is f of P. This is a solution within a normalization constant, right? So if I had been careful, if I'd put limits, I would have had like f initial down here at the bottom and it would have given me a constant out front. So yeah, here's where we have, I didn't even bring in my book. Turn to page 103 and you'll see some commentary on this. The first thing is normalization. How do you normalize a function? Okay, so I'm just going to put the a out here, the normalization function, or normalization constant to be complete. So how do I normalize that?
1 equals the integral of complex conjugate.
What am I integrating over? No, what variable? I dropped it off. FP is a function of x. So I'm going to integrate over x. So I do that integral. X, that's not an x. So I have something like that. Now I put P star, but really P should be real, right? And so if P is real, it collapses down to that. And can I make that integral equal to 1? Well, the integral of dx is x, going from minus infinity to plus infinity. So I put in the upper limit, I have infinity minus my lower limit of minus infinity. So I have to infinity and beyond. It's not normalizable. And so that's kind of a problem. It's kind of a problem because we have a function that I can't normalize. It doesn't represent a real state. But if you look on page 103, it says, but we can do something kind of cool with this less. We can say, well, making sure we restrict ourselves to real momenta, no imaginary momenta. So P star will disappear and we'll just have P, which is what I did in that step. We can say, well, what do we get if we do f of P prime FP? if this is a normal standard correct wave function, what should I get when I do that calculation?
Isn't it actually two?
I should get 0. Yes, the prime means it's a different p. So I should get 0 unless p equals p prime. And then I should get 1. Now this is a continuously varying p. And so this is going to be I didn't rewrite because it's fundamentally the same integrals I had up above. Probably should change colors at least. But it's fundamentally this same integral, except for I have a p prime for the first one. So the negative exponent is a minus p prime. And so that I combine them into the same exponent here. And you look at that and you're likely to say, well, that's going to be interesting, but, well, look on page 77 of your text. Do you either have a textbook? I know I left mine in my office. Well, if you look on page 77 of the textbook, I have to get it because I don't have this memorized. I looked at it before class and I'm good. So page 77 of the textbook says, and you look at equation 2.144, it gives us a definition for the delta function. Was that the Kronecker delta function? And it says that, so putting in different, and so now that I've given it to you, you have to dictate to me.
Integral from infinity to infinity of e to the ikx dk.
Okay, so now how is this relevant? I did write it correctly, right? How is this relevant is the question. Well, if we look at this, the integral is over k. So k is going to take the place of the x in our integral. Right? We have to be a little flexible. And so that means that x must be taking the place of p minus p prime. And we do have an h bar to put in here. So technically, I suppose, my x in the blue equation is going to match with that. And so what this means is that I should have Kronecker delta of p minus p prime over h bar is equal to 1 over 2 pi minus infinity to infinity to the I it'd be like that, right? Doing direct conversion. Now, I've got this h bar in here. It's still going to be 0 if p is not equal to p prime, but it's going to make a difference if I go to somewhere else. So this h bar actually needs to be taken out of that delta and moved back to the other side. So the question is, how do I do that? Trying to think about that. I In 2 minutes, I'm not going to get there. So let's look back at page 108. I think it's 108. Actually, up top. 103. 103. 108 was the next problem, which clearly we're not getting to. So looking back here at page 103, you can see we've gone through and done this mostly like we have, but there's H bar. And so what we end up with is this equation. That is, we can write F with a kind of normalization constant out front that we got from doing this. And so what was that normalization constant?
1 over the square root of 2 pi h bar.
Yeah. And that h bar in the square root comes from that h that I had in my delta there. Right? When to get it out of the delta, it ends up going into there. Right? Because there's no h in what we have written other than inside the delta. And the rest of it was just that, right?
Yes.
And so we do have a function here that is quasi-normalized. And then he says, and it turns out, even though it doesn't represent a real stationary state, it really has the properties that we need. It has, a quote from him, that wasn't the origin. Let me say somewhere here. He says, fortunately, this is all we need, and goes on. I read it right before class, and now I can't find it to save my life. Well, we're out of time, so I can't continue on and do the next things. But here we have a continuous solution, right? The P's are continuous. And so this is not a single state that you have the first state, second state, third state. You have this function of P. X is its variable, but P changes as well independently to give you the different states, if you will, continuous states. So we'll continue with that on Wednesday.